Okay, welcome everybody to the final, penultimate, I think. Penultimate, we've got one session next week. Welcome to today's BPHO Computational Challenge. Today we'll be discussing epidemiology. So even though this doesn't sound like physics, there's a wonderful thing about physics being that if you have equations, you can describe and model the universe. And what sort of techniques you can use for modeling bits of physics are exactly the same techniques that you can use in modeling biological systems. And indeed, there's a very big area of biophysics which has grown in the last 10, 20 years. And one of the big regrets I have when I studied at university is I didn't take more biology. I could have taken biology, ended up not doing it. Maybe this is an opportunity for you to see the wonders of mathematical modeling within a biological setting. So, Dr. French, go ahead and talk about
Thank you very much indeed, Professor Chung. Good evening, everybody. Welcome to the final session of the main course. We have our concluding session next week, where we'll be talking about all sorts of different challenges from the perspective of our fantastic Oxford University PhD students. So you can hear a fresher voice than me next week. So we're going to conclude with epidemiology, which, thank goodness, this isn't at this present moment the topic of the day. Of course, all of us have lived through the COVID years, so 4 or 5 years ago, where this was what everyone was talking about. However, alas, this challenge humanity will face again and again and again. So I think this is a really good place to end this course, because in some ways it's where my own involvement with this kind of thing kind of began. So myself and a colleague at Winchester, Dr. John Collern, were working on mathematical modelling of the story of Eyam, which is we'll talk about in a moment, but in 1666, the plague village in Derbyshire. And we wrote a paper with some students on this. And it's actually, the whole thing came from a play. So it's really kind of cross-curricular kind of stuff. And then, of course, the COVID struck, and Dr. Clone actually masterminded our sort of COVID response. There was heroes in every school, and he was one of ours. So we ended up, actually using some of the ideas that we'd written in our paper to help not solve COVID, of course, but to understand and to what was going on. So here we go. So let's have a little look. And usually, as we normally do, we'll sort of pause at various points to sort of show you how you can code these things up at various levels. So we'll look at Excel, we'll look at a MATLAB GUI, and also we'll look at some Python as well, which is the sort of first system that I put together. Right, let's give this make a start. Okay, so this is the sort of the whole story. As usual, we will dip into this. So we'll talk about the 1665/66 plague of the village of Eyam in Derbyshire. And then we'll start to develop the Eyam equations, which are a set of 4 equations which describe epidemiology, which is all about susceptibles, so the group of a subset of people who are susceptible to a disease, the infectives, the subject who have the disease, the recovered, or possibly the dead. So that's 4 groups of people, and just like sort of vials of fluid or different states in thermodynamics or all that kind of thing, we're going to develop equations of the flows, the population flows between the susceptible S, the infectives I, and the removed, which will be the recovered or indeed the dead. And then we'll start to talk about how we might use numerical methods, and indeed what that means about Ebola, which is how we started to apply this model. And then we might talk about COVID-19 at the end to conclude. Right, so if you have any questions about the actual challenge for this year, if you can reserve those to the last sort of 10 minutes, I'll take some Q&A on that. But we gave a good briefing on this, the optics challenge of this year, indeed the optics of optics, last week. So I do encourage you to look at the video for that. But I will take some questions if you have them. But yeah, please don't sort of have questions mid-talk. Let's focus on epidemiology for now. Okay, right. So let's start with 1665. So physics, I think, is all science is best told via stories. And what's really lovely about physics, it doesn't really matter which story you pick. It kind of contains all of physics. It's rather fractal. And this is the concept of my book, Science by Simulation, is that we pick a good enough story and then we can use that as inspiration to learn some science. So what is this story? Well, it's rather a gruesome one. This is the church in Eyam in Derbyshire. This is Yersinia pestis, which is a bacteria which basically carries the bubonic plague. And the vector for this is mostly fleas. It's probably not the rats, actually, that you might have sort of in sort of popular memories, sort of like the plagues of London. It's probably more likely the fleas. So because the Yersinia pestis bacterium lives in the blood of the fleas, you see, and then the fleas bite other creatures, and then the plague is passed on, including humans. So it's thought that George Vickers, the tailor's assistant, got some cloth from London. And it was damp, so he dried it in the fire, but next to the fire, and the fleas which were alive were released, spreading the pestilence in the village. And it's a horrible situation. Almost about half people died in the village. But this chap here was a real hero. He's a guy called William Mompesson. Now, he didn't manage to save anybody, but well, in the village anyway. But what he realized is that he should take good data to find out who's got it, who might get it, who's died. He wrote this in the parish records. So every week we've got an idea of the populations, the susceptibles, the infectives, the recovered, and the dead. Now, sadly, for the plague, nobody recovered because, this is the 17th century. Nobody knew about bacteria, certainly not antibiotics. But they did know about quarantine. So they quarantined the village and no one could get in or out over the several months of the plague. And they sort of had this sort of innovative system of getting food in and out of the village, or mostly into the village. So what was amazing is they didn't spread the disease to the nearby towns and cities. So although it was a tragedy for Eyam, it could be an even bigger tragedy for the cities nearby. So this guy's a real hero, but it's his data which we're going to find useful today. Okay, so here we go. Here's a bit more context. So if you don't know where Eyam is, it's in the middle of the Peak District. A very beautiful place. I actually went there a few years ago. There is a museum which may or might not have my paper in it. So there we go. George Vickers, the tailor's assistant, Yersinia pestis. So the idea is from William Mompesson's data. Okay, we can plot this on a graph. So that's kind of our tool, isn't it? We've got some observations in numerics. The first thing you want to do is draw a diagram and plot a graph to use our sort of visual cues. Okay, so I've got infectives, which is the red curve. I've got the dead, which is the blue curve, and I've got my susceptibles, which is the green curve here. And remember, the blue one is cumulative. So you see some immediate shapes. You kind of see an S-shaped curve for S and D. And for D, we could talk about recovered as well. For something like COVID, thank goodness, it was a relatively small fraction, a mortality fraction of maybe something like 1%, depending on the certain groups who got it. Thank goodness for that. But that's still an enormous number of people. I think for the UK, it was something like several 100,000 people who lost their lives. And worldwide, it would be in the millions. But when you have things like the Spanish flu, which is probably the largest disaster in modern memory, but when we think about the Black Death, it's thought to over several hundred years, half of Europe's population expired due to this disease. So the Black Death is basically Yersinia pestis. So thank goodness we have antibiotics, eh? So you have some shapes of the curve. And the idea is that once we start looking at the shapes of these curves, we start thinking with our mathematical hats on. So what do we see? Well, we see a kind of peak to the infectives. It rises, reaches a peak, and then diminishes. So that kind of thinks, well, this is about calculus. This is about the gradients of things. Does that tell us anything about this infection? Does it tell us about I, S, and D in general? So maybe other diseases. All right, can we model the flow of Ebola or anything, monkeypox, flu? All right, can these be modeled in a similar way? And also, you then have the sort of the cumulative graphs which follow these curves. So in other words, can we predict these curves? What does that tell us about the disease? And you'll notice in the graph, it's got some parameters here. So we've got an alpha and beta. What do these mean? These are characteristic numbers of this pestilence. And Ebola will have different numbers. DT is the time step. So this is a numerical method. As it will turn out, sadly, you can't solve the Eyam equations directly. You have to use a numerical method. So you can't just integrate stuff. So it kind of implies that we need to have differential equations, an equation involving a derivative, a rate of change. And in fact, that's common to pretty much all the laws of physics. I think Newton's second law, mass times acceleration is vector sum of force. Well, acceleration is the gradient of a velocity time graph, and velocity is the gradient of a displacement time graph. All right, so everything's often defined in terms of derivatives, which then, if we can, we sum up or integrate to work out what we want, like, a particle, where is it in t seconds? So our simple model involves this sort of flow from susceptibles, people who might get it, to infectives, people who've got the disease, to the dead. All right, it's a really gruesome one, I'm afraid. But you might hopefully have something which infectives go to recovered. Now, of course, you can then make this more complicated. So recovered could then become reinfected, etc., etc. But let's assume there is a sort of constant flow. And in many diseases, the body has an immune system. So once it's become infective, maybe it can't be infected again by the same virus, that kind of thing. So there we go. Can we develop a mathematical model to predict I, infectives, S, susceptible, D, dead versus time? And what does this tell us about epidemiology, the study of epidemics in general? So epidemiology, not the study of the skin, that's epidermis stuff. All right. Epidemiology is about populations and usually associated with disease. All right. So it's actually a numerical topic, which I had no idea about until I started looking at this. So this is very much, as Professor Chung said, something that is within the realm of applied physics. Okay, and so what kind of techniques do you need to understand this? Well, guess what? Pretty much everything you learn at school maths. So calculus, differential equations, numerical methods, lines of best fit, iteration, loops, so all the stuff that we've been covering on this course. Right, so let's make a start, shall we? Oh, there's me, and that's an enormous flea. Not to scale, obviously. That would be really scary. So there we go. That's St Lawrence's Churchyard in Eyam. There we are. There's my little paper, which was published at Physics Education a few years ago, and it's the first chapter of Science by Simulation. So there we go. Right, some gruesome pictures to set some context. So Yersinia pestis is named after Alexander Pestis, this chap here. So he's a real hero. Looks like a hero too, really. It was the Hong Kong plague. Of course, it was the same thing as the Black Death. But of course, at the time into the late 19th century, they were able to isolate it and figure out this was actually a bacteria. And that's what you find inside fleas. So there we are. Alexander Yersin, 1863 to 1943. So there we go. Here's a very sort of sad looking flea with the blood meal containing Yersinia pestis. And this is your sort of healthy flea. All right. Now, some gruesome pictures. So firstly, the pathways for plague. So most of it, as you can see, these are the vectors of how the pestilence has been transmitted. And you can see it's quite complicated. In fact, there are multiple forms of plague, the pneumonic plague in the sort of lungs, and the bubonic plague, which affects the lymph nodes. And you get these horrible sort of buboes. And it can be passed, of course, by other animals as well. But the main thing is via fleas. So the fleas infect the rodents, etc. And then the rodents might infect you. So really, you can kind of look at the fleas as the major vector, really. Right, here's a nasty picture from the past. And these swollen nodes, these lymph nodes, right, is what the sort of is representative of the bubonic plague. And in those days, if you got those, I'm afraid that was it. There we are, some more pictures of grimness. And here we go. Thankfully, this isn't real. Sorry if you just had your tea. So this is sort of people who like dressing up as zombies, etc. But that's kind of what a bubo might look like. And this is from one of the museums. I think it's the one in Oxford. So pretty nasty stuff. Anyway, that's actually a real picture. So this does still exist in the world. But thankfully, we have antibiotics. This is why, everybody, we need to invest in continued antibiotic development, and we shouldn't really be feeding it to cows to make them bigger and that kind of stuff, because we need antibiotics. This is the sort of nasty stuff. Anyway, let's not dwell on that one, but that's what a bubo looks like. Right, let's look at some data, much nicer. So this is obviously sort of sanitized, sort of interpolated data. So the first thing you might want to do is get some, to turn the dates from William Maupassant's book, turn those into a decent time scale. So we're going to go for months, all right? So between 0 and just under 4 months. And we're going to plot the susceptibles, the infectives, and the dead. And then we've got some other columns too, which I'll explain why I've taken the natural logarithm a bit later. But you might understand the last one. It's literally the sum of the infectives and the susceptibles subtracted from the original population. So the number of infectives at time 0 and the number of susceptibles at time 0. So in this case, we started our recording where there was 14 and a half infectives. Now, obviously, we're not having half a person here. So what we've done here is we've sort of like averaged over 2 days to make the half. Only statisticians have 3.5 children, right? Anyway, so this number here is the original number minus the number of removed. In this case, the number who've died. So if we can plot this, we can start to see the peaks of our curve. And if we want to make a smooth curve that underlays this, this is what we're aiming for. Okay, so before I move on, are there any basic questions? Right, some registration things. Anyone in the Q&A? Anyone in the chat? Don't think I can see anything so far. Can you hear me all right still?
Yeah.
Brilliant.
Can I just quickly say, sorry, about the registration? We are looking at what's happening and why you can't access it, so we'll tell you in a bit. Sorry about that.
Right, fantastic. Well, we appreciate the keenness as well. But yes, you can download all the materials now from the Eclecticon, and but yes, do please register first. You need to register before you can enter the challenge. But you can download the data right now if you wanted to. But let's do that after this talk. Okay, so we're going to talk about the EAM equations. So there are 4 of them, and these are they. They are, well, 3 of them are gradients of the S, I, and in fact the R plus D curves. So in the case of our EAM situation, R is going to be 0. So the rate of change of the dead, the rate of change of the susceptibles, and the rate of change of the infectives. And this one, I think, is nice and easy to understand. It's basically all the populations added together are the same. So what that means is we've not added anybody into the village of EAM. It's been quarantined. No one's allowed in and no one is allowed out. Obviously, some of those people may have expired. That's the D population. And we're assuming that everything is just too grim for anybody to be born. Okay, so there we are. Let's have a look at the data. So in other words, what is the simplest model that describes the key features of our graph? And this is kind of Occam's razor. You know, what's the simplest thing that we can say that gives the essential features? And if that kind of gets you about 70 to 90% of the way, brilliant. All right, because we can do something with that. And we can always make it more complicated later. But if you start putting all sorts of parameters, you know, essentially you'll have very little idea about what's going on. And you won't know if you code it up in a computer if it's just numerical noise or not. So I would strongly recommend almost all of you, if you're going to do some physics in the future, professionally or in your research, it's very easy to sort of, you know, get an off-the-shelf AI system or something like this, and nobody has any idea what's actually going on inside that box. And so how do you know the solution you've got is real? So I would strongly recommend using a piece of paper and a pen and maybe a little spreadsheet and code up a model that you understand all the features of. And then you can compare that to reality and go, well, you know, have I understood the basic features here? And that's really, I think, the essence of almost all of physics. So let's go and do some maths. So what we're going to do is propose the following. Let's look at the top boxes first. So a bit like radioactive decay or Newton's law of cooling, that kind of stuff, or possibly capacitor decay, if you've got that there so far in the lower sixth. If you're in the upper sixth, you'll know all about this, is that the rate of change of the dead, so in other words, how does the dead population grow? That's going to be proportional to the number of infectives. So more infectives, we're going to expect to get more people who will eventually die. And we can kind of think about a sort of time constant for this. It's a bit like, you know, the activity of a radioactive source depends on the number of radioactive atoms we've got. All right, so it's a bit like this. and the constant in front of it will be the sort of activity, the sort of related to the half-life of the source. If you've got a source which is, has a very short half-life, you're going to get a very steep curve. So in this case, if alpha is very, very large, the infectives to dead change is going to be enormous. All right. And also, if you think of the units of this, all right, this quantity alpha will have units of 1 over time. All right. So if you can define a kind of time constant from you've got it till you're likely to die, then 1 over that is going to be what alpha is. So that's a very useful number to know, because if that number is, well, hours, then that's a big problem. Because if you get the disease, like say you're sort of zapped by some sort of neurotoxin from a nasty frog or something like this, then you haven't got time to go to the hospital. You'll already be dead. So, if you are in the sort of environment where you might have a very fast acting pathogen, you need to have an antidote on site, like for snakes, etc. Whereas if you get a pathogen and it takes about 3 weeks for you to die, you've got plenty of time to get to a hospital and do something about it. Right, let's look at the susceptibles. And this is where the mathematical interest really comes in, because the rate of change of the susceptibles should be proportional to the infectives. If I've got double the number of infectives in my village, I would expect the susceptibles to rise faster in proportional to them. But obviously, if I've got, say, 200 people rather than 100, the rate of change of my susceptibles should be proportional to that as well. So ds by dt is going to be proportional to s times I. Now that's going to make things interesting. And why is it a negative? Well, obviously my susceptibles are decreasing because they're becoming infected, whereas my dead population is going to rise because it's proportional. So, so that it goes, that's the flow, if you like. So the sign of my derivatives is determined by the arrows of my flow here. Okay. Now, I've also suggested that for our system, we're going to set r equals 0. But in general, you could say d be some constant times r plus d. And that's the k is what we call the mortality fraction. Okay, so we could generalize this to a disease where, hopefully r is much, much bigger than d. So k would be close to 0. But let's have a fixed population constraint. Now, obviously, if we were applying this to the UK during the COVID times, particularly at the beginning, our border was pretty porous. Right, we were a bit slow. I don't think I'm saying anything too outrageous there. I think that's a fact, isn't it? Compared to, say, for example, Korea, we didn't lock our borders very, very quickly. Countries like that would have had experience of things like SARS. So hopefully, if this happens again, we will, learn from our mistakes and close our borders and fix that population. And that will actually, as you'll see, will depress the growth of the epidemic. But let's say EAM's actually, it's not a good example because it's an awful example, but from a sort of case study, it's very important because not only do we have good data, it's actually a fixed population. So if you do work out the derivative of all these terms, obviously the derivative of a constant 0. So we expect the sum of the derivatives, di by dt, ds by dt, and dd by dt, all to sum to 0. So if I combine that with the first two EAM equations, I've now got an equation for the rate of change of my infectives. All right, so it's literally minus this one, minus this one. So if you work out through that, that's beta si minus alpha I, and we can factor out the I from that. So there we go. Let's just have a little look at this. So what that means is we've got something in front of the infectives which could be positive or negative. And what that means is that's going to tell us whether our infection is going to grow or not. So in other words, we expect I versus T to have a peak with it. So we've not even done any integration yet. But from this differential equation, we can tell that we're going to rise up to a maxima and then diminish. Well, as long as that has a potential to be negative or positive. So in the box here, what we can say is, well, if that thing in brackets is positive, right, then S is going to be bigger than alpha over beta. So this ratio of these rate parameters, that remember I've defined in this way, all right, is actually a threshold. It's a number. So if our number of susceptibles is actually bigger than this number, all right, our epidemic is going to grow. If it's less than this number, the epidemic shrinks. So immediately we can see if we can reduce the susceptible population based on whatever this ratio is, we might not get our epidemic to grow at all. And so things like quarantine and staying at home and all that kind of stuff, that's what this is all about. Okay, so if you want, I put on the back some slightly smaller type for calculus fiends amongst you. If you differentiate that again, you'll see that it's less than 0 when evaluated at alpha over beta. Okay, so that's when it's maximized. So when S is alpha over beta, di by dt is 0. And that's the second derivative is negative. So that's definitely a peak. But we kind of knew that anyway. So the math just sort of confirms what we know intuitively. So there we go. That's a good start. Those are our 3 EAM equations. All right. Do we have any questions before I talk about how we might solve those?
No, not right now.
Okay. All right. Okay. So here we go. So here's solution number 1. So this is kind of this. So I remember this very, very well. I was speaking to my friend Dr. Klearn at Winchester about this project. He was telling me he'd sort of started building a model in Excel. This all came from a play he did. We have in our school at Winchester called Div, and it's all sorts of things. It's sort of combined humanities, and he was doing a project on human suffering. Which hopefully won't. That's not how my students view my physics classes. Well, if you do, never mind. Sorry about that. But anyway, on this sort of project of human suffering, they looked at the Roses of Eam, which is a really good play about the Eam pestilence. And of course, Dr. Klearn, being a top quality physicist, decided that we can't resist by teaching a bit of calculus here. So, but the nature of it was we had people who weren't doing A-level maths. So how can we get away with teaching calculus without actually teaching calculus? So the idea is to build a spreadsheet. And so this is what we did. What we're going to do, though, is sort of take one step beyond this. And I decided to take this on and build a Python program and build things in a loop because that's a bit better than a spreadsheet. So what we're going to do, what we're going to try and do is solve our EAM equations iteratively. And the simplest way of doing that, and this actually is a completely general integration technique. You may not get many points if you are asked to, I know, integrate the hyperbolic sine of x or cos of x squared or something like this. But if you want to try, you can integrate anything you like this way. All you need is a spreadsheet. So what you do is you say, all right, let's say if I've got my derivative ds by dt, the first one, the change in my susceptibles is minus beta si times a change in time. And the idea, which goes back to Leonhard Euler, the Uber mathematician from Switzerland, is to basically have a fixed time step. Now, it's important to know there are more precise ways of doing this. The trapezium rule, the Runge-Kutta rule for integration, all sorts of things, Simpson's rule. The simplest thing, though, is to take a finite time step and to think about derivatives as fractions. So what I'm going to do is I'm going to work out what alpha and beta are, more about that in a moment. So these are the parameters that I've worked out for our EAM pestilence. These are the initial parameters, the initial conditions that we've got from Montpesson. So 235 is our initial number of susceptibles, 14.5 is the initial number of infectives, and the dead count starts at 0 when time is 0. And what we're going to do is we're going to iterate time like this. So every delta t, which I think I set as 0.05 months or something like this, we're going to increment. So after in delta t increments of time, we're going to take away beta si times delta t. So that there is delta s from s. So Sn plus 1 is Sn minus this lot. And you can do the same for all of the others. That's something, ladies and gentlemen, we can code up in a spreadsheet. So here we go. Although actually in my presentation, we're going to do it in MATLAB first. So there we go. So that I think, because you can kind of see the code version of this a bit more clearly if you do it in an iteration. And by the way, just as a link to the challenge, so we've made the rules a little bit harder this year because we had so many gold responses last year. So to get a silver, the rules are you have to make a good attempt at all the problems in code. Okay, so if you just do the spreadsheet ones, that could be an amazing bronze. But if you want to get a silver above, you need to have a go at coding, please. And gold means the extension stuff. All right, so we've sort of we're upgrading it a little bit because again the responses have been so amazing. So this is how we do it in MATLAB. And again, it doesn't matter. It's going to be very similar in Python. I'll show you that shortly. So this is a function. So what we want to do is you want to output vectors of time, infectives, susceptibles, and the dead. I'm going to call it something. It's called the E model. And my inputs are my time step, my initial infectives, my initial susceptibles, these two parameters, which happen to be 2.894 and this one, and my maximum time, which might be, I don't know, 5 months or something like this. So what do? Is I initialize my output vectors, and then all I need to do is step through and work out my iteration. So if you kind of eyeball this for loop, all right, so the thing in brackets, that's just the next vector or the next element of a vector. Multiplications of stars, etc. That kind of looks like this, doesn't it? All right. So using a high-level language like MATLAB means your code looks like maths, and Python's very similar. So if we code that up, we get now. If I just show you what the picture looks like, it looks like this. There you go. Right. Oh no, that's horrible pictures. Let's not look at that. All right. So if we were to run that in code, and I think what I'll do is I'll just show a little graphic, a little GUI, which I've made that implements this. So if we go out and look into MATLAB, here we go. Hope you can see that. Just put this one here. So the crosses are actually Montpesson's data. That's what this button does. But what I can do is I can vary the alpha and beta parameters. But I've used my loop to actually sort of solve this, just to show that something's going on. If I change my initial infectives, I move that up. Right, you can see the graphs move. Okay. I think I might need to reset that. Oh, that's not too bad. Now, if I change the alpha and the beta parameters, you can see how the curves dance. So if I make alpha, which is the rate of change of the dead, right, the blue curve gets much steeper. And you'll find the red curve then drops off more. Why is that? Well, because more of the effectives are becoming dead. And then the susceptibles are also diminishing. That gradient changes. If I change alpha over beta, all right, that's going to make it a bit more shallow. So this is the kind of control I've got for changing alpha and beta and alpha. All right, so you could look at any general form of epidemic by varying these parameters and see what happens to the curves. But obviously, we want to try and match this. So what you do is you sort of set the alpha parameters. What are they? About 163, I think. Something like that. And alpha, I think, was 3. There we go. So what you can do is you can kind of do almost like a dynamic curve fit. More about that later. So how do we find these optimum parameters? So obviously we could just sort of move these sliders tediously and trying to do this, but is there a better way of doing it? So let's go back to our presentation. So what we want to try and do is, can we do some analysis? Can we use some calculus to help us here? So there is something you can do immediately. You can solve this a bit more, but that gets a bit more involved. I'll refer you to our book for that. But this is something I think if you've done a first course in sort of lower sixth calculus, I think this should be all right. So if you haven't met the 1 over x integral, then this might be new, but I know a lot of you will have done. So let's look at our equations, and what we're going to do is we're going to eliminate time. So we're going to see, all right, how does s and I vary? Okay. Because I might think, well, I can't integrate this straight away, but maybe I can find s in terms of I. So if I do delta I over delta s, right, so we'll literally divide this one by this one here. I've got beta si minus alpha I over beta si minus in front. And if you have a look carefully, we've got the that sort of bit cancels out. So I've got a minus 1 here, and I've got alpha over beta. The I cancels, and I've got 1 over s. So if I integrate this, if I find out what I is, so if I sum the delta i's, that's I minus I naught, and I sum the alpha over beta 1 over s minus 1, that's my integrand, I get a log, a natural log, and an s here. which I can integrate. So I can analytically predict how my infectives vary with my susceptibles. Probably ought to have a bracket there for pedants. And so the thing you want to be looking at in physics is that, well, in fact, let me ask you that question. I've not asked you guys a question yet. So the big hints in the box there, but what is the key analytical tool that we have in experimental physics? Hint, hint, plotting a graph. What kind of graph do we want to plot? Let's have a look. What does it say? Still a lot of people asking about the links. Yes, a product moment correlation coefficient, scatter graph, well done, a linear graph, an exponential graph. Well, that's a good idea because it's got a log in it. But what we're trying to do is linearize our function. So whatever our model is, and we've got a log here, yes, we could exponentiate that. But basically, we want to do a straight line scatter graph. Because if our line actually is a straight line, and we can do something called the product moment correlation coefficient, which is a measure of how close our data is to a straight line, we can see whether our model is correlated. And if it is, then we might have from the intercept and the gradient some information. What do we want to find out? Alpha over beta. So if I define, so I can rearrange this any way I like, but alpha over beta is clearly the parameter I'm interested in. Well, actually, I'm interested in alpha and beta separately, but I only get the ratio. Okay, fair enough. So let's rearrange this such that alpha over beta is the gradient of my graph. So if I say x is the log of s naught over s, why have I done it that way? Well, so I can have some things that are positive. So if I basically move that to one side, the minus of this one is, of course, s naught over s. Okay, I hope that's all right. So what am I doing? Yes. So basically, what I've got is this quantity here, alpha over beta x, I'm predicting equals y. And y is essentially the number of dead, right? It's the original population minus this the current I and s, all right? So this could be, we could say d is alpha over beta x, basically. Now, so what I can do is I can plot that with our EAM data. And indeed, this is what I've got on the graph. So, and I'm going to do a line of best fit, and that'd be a nice thing to code up. You could do it in Excel. I know we've got, what, 1, 2, 3, 4, 5, 6, 7 data points. So this isn't going to be the greatest correlation in the world, but it's a pretty straight line graph. I was rather excited. Actually, there's an extra one here because it's 0. So I was doing this at the Brighton half marathon in a pizza parlor with on my laptop. So I was very excited when we managed to code this up. And so I was able to find out what alpha over beta is, which is about 163. So we now know what's alpha over beta, but what we really want to know is alpha and beta. So remember, if we go back to our little presentation here, our MATLAB code, all right? So I could probably put in alpha over beta. So was it 163? All right, and then I could wiggle my alpha parameter. So if I make alpha too big, well, that's rubbish. That's going further away. Let's make it smaller. Well, that's quite close, isn't it? 3.1. Well, that's a bit too far away, right? So it's going to be about, oh, it's almost close to pi. So that's quite close. And then what I might do is I might start wiggling these numbers. So what I really need to do is now find some measure of how close my predicted curve is to my data. So I use the same method that I do for lines of best fit. In fact, if you've ever done the mathematics of this, what you do is you look at the sum of the squared differences from your data from a line, and you try and minimize those, and that tells you what that line is. Now, there's actually a formula for this. It's what's used in Excel to find your product moment correlation coefficient, etc. That's not really something that we can have a recipe for. So we're just going to might as well do it in a loop. So this is where you want to go away from Excel and do things with a program. So basically, oh yeah, by the way, this is the line of best fit function. You can download this and have a look at all those things, but it's not too difficult. And this is basically what I did. So I worked out, I ran my code. Remember, this is the code for it here. I ran my EAM model. I know what alpha over beta is. So what I do is I have a range of alpha. Now, what is alpha? Well, if you look in the literature for diseases, remember this is going to be to do with the sort of the time constants. 1 over that is roughly the time in months that you might die given the disease. So you can kind of work out a sensible range for what alpha might be, maybe between say 0 and 4. So basically what I decided to do, actually I went from a bit closer around 2.7 to 3.1. So I had a range of guessed alpha values. I then ran my model using my value of alpha over beta is 163. And I found for each of those data points, I worked out the difference between my curve, my predicted curve, oops, I've got one there, and the actual susceptibles. So M is the model, S is the actual data. I squared all of those and then added them up. And then when I do a sum, so I call this the sum of squared differences. And then what we're going to do is plot those. So you have to do this in a loop, but you can do that very fast in code. And the bottom of that curve is what I deemed alpha to be. So that's the alpha value that minimizes the sum of the squared differences. And it turns out it's 2.89. So let's go back to our little MATLAB model. And so if I put 2.89, you'll see that that has really quite a nice fit for all three. Okay, you could maybe prioritize one of the curves. And in fact, we might briefly look at how it works for Ebola, where we only have the infectives. And in fact, that's true for COVID as well. We might have the dead curve, sadly, but we don't have the infectives. All right. So in most situations, you only have one of these. But in EAM, of course, we had everything. So there we go. So that's a really kind of general purpose solving method, which is using lines of best fit, all right, to find alpha over beta based on this sort of analytical relationship between I and S, and a sort of general purpose model where we can look at the sum of the square differences. And so if you put that together, this is the sort of optimum. Alpha is 2.89 and beta is 0.0177. So there we go. And I did that as a model with 0.1 months. So that gives us the time constant 1 over alpha is about 10.5 days. So that's a crude measure of how long you've got, essentially, if you were to get bubonic plague in the 17th century. So that's a very useful number if you were modeling another kind of epidemic. So just briefly, we'll look at how this might be coded in Excel and then in Python. So here's the Excel version. So this is the first thing you might want to do is you've got your table here and you just plot it. And remember, I've got the log of S0 over S versus our numbers of the dead. Okay, so you can see these columns match each other. And there we go. You can see our straight line graph. That's a line of best fit. To find a trend line in Excel, you right click and you can sort of add a trend line. So if I maybe get rid of that, if I get rid of my trend line, delete the trend line, right click, add a trend line, and you can sort of display all the equations in it. All right, maybe set the intercept to be 0. So there we go. You've got 163.29. And then for the model itself, what we've got is all my inputs here. And I've gone for a very small number of months. And if I sort of, these are my original values. And then my next one down, if you can sort of see in the box here, I've got C14, so the previous S, plus F11, which is delta T. And then I've got my delta S. So it's kind of harder to see, but basically we've got minus beta SI in the brackets. Okay, so I'm doing that. That's what I work out for the next cell. Then I iterate that down. So using Excel, we can actually apply our iteration and we can solve or indeed integrate these differential equations. All right. So basically, this is sort of fixed by the time step. If we go back to the MATLAB, actually, yeah, we'll go back to the MATLAB model briefly. And if I increase the time step, you can sort of see what happens. So actually, we start to get a worse prediction. And eventually, you'll start to see it getting really sort of, yeah, there we go. You can sort of start to see the lines becoming rather crude. All right, so the time step we can change. All right, okay, so let's just quickly look at what that looks like in Python. This is, I'm using Visual Studio to kind of represent this. You know, the trick is finding the development environment that you like. I'm not so keen on actually Visual Studio. It looks quite good, but it's not so great for running things, I find. But you do have this thing in the corner, which you can sort of navigate your code. So in Python, it's kind of similar. The hashtag means commentary, and sort of I'm defining all my various parameters here. And here we go. Here's my EAM model, and it looks very, very similar to what we saw in MATLAB. We've got a range, but the for loop in Python, you don't have an end to it. So that's just sort of how the syntax work. You say n in range 1 to n colon. So it's a little bit more cumbersome, but there we go. And brackets, square brackets are what array elements in Python. So otherwise, it's very, very similar. And then you have to return a value of a function. That's how you define it. So it's basically the same kind of stuff. You just have to learn the syntax of your code. If you do it in C or JavaScript, you'll have a slightly different way of writing it. So there we go. So I've got things like the best fit function. I've got things like, this sort of plotting thing. That's the sort of main function here. And, a lot of this sort of stuff is all about the plot commands and how you actually make your graphs. So there we go. So if are any more questions, just by the way? So time is probably got about 10 minutes. Still people asking the link.
All good.
Excellent. Right. So I think what I want to do is there is I'm just going to put one slide on this. So just as a sort of a food for thought, because it gets a bit more mathy here. But essentially, there is a very famous equation for this by Kermack and McKendrick, and it involves a Sech squared function, a sort of inverse hyperbolic function, which predicts the red curve. Okay, but it's not quite right. It's not actually as symmetric as this. But this was sort of set up in 1927, and it lasted for decades until people actually started to use computers and realized this isn't quite how epidemics work. But it focuses on the actual infections themselves. And so we kind of sort of, in our second paper, tried to explore, can we push the mathematics as much as possible? And indeed you can. So this may look rather horrendous here. It's involving all these logarithms. But essentially what you have to do, the thing I'm circling, is you have to evaluate this integral, right, for time. And it's involving dimensionless parameters, which, and if you can sort of see, there we are. So you have, you all set sort of time, a dimensionless time array called tau, and that can be negative. So you set the time based on the time where the peak of the infection is. So basically you fix your curve to the top of the red curve. And then what you can do is you can work out the infectives, susceptibles, and deads via these sort of dimensionless parameters. And it all boils down, and this is a lovely idea that my colleague John Kern figured out, to this dimensionless parameter, which goes between 0 and 1. And that kind of defines the model. So it's very similar to before, but we have slightly different input parameters. So rather than alpha and beta, we have alpha, eta, this thing here, the maximum infection and the time that happens. So there's still 4 inputs, it's still the same equations, but we change the inputs. So because alpha over beta could be anything really, whereas eta must be between 0 and 1. And that means you can fit the curves more generally if you only have infective data. So we looked at Ebola, and I'm just going to skip ahead, apologies for this. So this is what Ebola looks like, a horrible thing. It looks like a serpent on a microscope, a really, really nasty virus. And there's an outbreak in Sierra Leone, I think in 2014, something like this. So this is from the World Health Organization. And basically, this is the data. You think, is this one of these infective curves? So what we tried to do is, can we actually figure something out about Ebola just from this data set? So what we did is we plotted it, Liberia, apologies, not Sierra Leone, over 2.5 months. So this is the data. We sort of figured out what the infectives versus times are. And then we've got the sort of more advanced model, which has lots of other parameters, eta, alpha, Tmax, and Imax. And I basically did a curve fit using a combination of techniques, but mostly in sliders, etc. to find out what the curve is. So this the sort of Kermack and McKendrick squared graph, the symmetric one, is this dotted line, but that's not quite right. A better curve is an asymmetric one, which solves the EAM equations. So for this one, we found Tmax is 1.6 months, Imax is 323.3, alpha is 2.94, and eta is 0.751. So these are the parameters that we've got here. And from there, you can work out some really useful things. So you can work out the number of susceptibles, because you're now solving the EAM equations, you have everything. You can work out the critical ratio, to get to the alpha over beta, which is 1.373. And importantly, you can work out the number in the population in the first place, which is 2,542. Obviously, that might not be entirely precise for this, but these are numbers which you wouldn't otherwise know. These weren't known, these weren't in the report, and yet you can figure them out with some assumptions, of course, based on the data you've got for infectors versus time. Now, this is really helpful. So obviously, the WHO will be using a much more advanced model, but this is something that involves 4 parameters. You can do a sort of rough sanity check of the data you've got. And importantly, it has something called R0, which is the basic reproduction number, which is essentially how many people do you go on to infect. And our numbers, about 1.9, is actually linked to the literature quite well. So we were rather pleased by this. So just this is what this color graph means. So if you plot Imax and Tmax and do a sum of squared differences for running this model in a big loop, but for thousands of ones where you're varying Tmax and Imax, you'll find that there is a minima to this surface, like a big hole. And that's the best one is at 1.6323.3. So we're kind of generalizing our kind of doing things in the loop, but for 2D. Obviously, ideally, you'd want to do it for more than for four parameters, but that's a 4-dimensional surface, which is harder to plot. Okay, so I've got not much time. So I think, are there any burning questions about the challenge? If not, I will give a very brief glimpse to kind of how we might use more probability for this, and maybe a little bit about what we did for COVID. Do we have any burning questions in the chat? If we are registering for the challenge in pairs, do we both have to fill out the registration form? I'm pretty sure that's just one of you, I hope. Is that correct? Can someone correct me if I'm wrong there? I think you can do it as a team. I probably should know.
You only need one, otherwise you're going to get lots of repetitions if you're not
careful.
careful.
Excellent, good. We don't want that. So you can be individuals or pairs, but no trios, please. Okay, so but do give both your contact details, please. But yeah, in principle, you don't have to be from the same school. I think most people are, so you can collaborate. But but yes, you can sort of work out your pairings. You could be anywhere in the world, actually. So, all right, any more? Right, okay, fantastic. So a stochastic model is when we roll a dice, because, if I keep cutting up time here, I can't have a sort of fraction of a person becomes infected. That's just not going to work. It's a whole person. So how might this work? So this involves something called the Poisson distribution. And this is a statistical distribution, which is about sort of the rate of, buses that come, or the number of goals per game in a football. It's basically a binomial distribution where the number of binary trials, like the number of kicks in a football game, is very large, and the probability of, say, scoring a goal for any given kick is very small. But yet the multiplication of those two things, the mean average of your binomial distribution, is a reasonable number. So that's the sort of limit. It's a limit of a binomial distribution. It's called the Poisson distribution. Very fishy indeed. Anyway, so what you're assuming is we're going to go through our model, but the number of the change of susceptibles to infectives is not going to be a fraction that we predicted so far. It's a whole number, with the mean of that being the change that we get from the EAM equation. So beta SI delta T is the mean number of infectives that will grow from the susceptibles. But we're going to have that as an integer. So what we can do is basically using a random number generator, pick from the Poisson distribution, and then work our model in a big old loop. So this is how it works. So this is the Poisson distribution. That's what it looks like as a sort of histogram of 100,000 samples, with the mean being 7.4. And why I chose 7.4. Oh, that's maybe a goals per game or something like that. That's a very, very exciting game, I think. And so what we want to do is get random numbers that, if you made a histogram of those, would look like this. That's a really nice little technique for another day. But that's what a Poisson distribution looks like. So if you have some coded up how we can sample from a Poisson distribution, given a fixed mean value, and interestingly, the mean and the variance for your Poisson distribution is the same, then we can generate. So I'm going to skip how we did this, and just to show you what we did. So we ran another loop, but this time the update, right, is our samples from the Poisson distribution. So we find lambda, which is the mean in this case, and I'm working out for my Poisson distribution what my change in susceptibles are. And I do something very similarly for my I to D, my infectives to dead populations. So it's it's almost exactly the same as what we've done before, except I now have this extra bit of code saying Poisson samples with a mean number, and that will give me an integer, which is if I have a histogram, will look like this distribution. But obviously the mean is based on this, so the mean changes in your loop. So what we do is we run those, all right, through time, and one of that will give you one of these little trajectories. I've got a bigger picture. Here we go. So one of these trajectories is what happens, and basically I run the thing multiple times. I think it's about 200 trajectories I hear. So each one has a sort of using a random pick, and you see that the sort of solid curves are the Mompesson results. Interestingly, the averages are slightly, so what was I got? The underlaid as dots, the averages, the black lines. Sorry, the black dashed lines of the Euler model, apologies. The solid lines, the averages of my stochastic model. And what seemed to be really intriguing, I've never quite got to the bottom of this, is these always are slightly lower than what the Mompesson model predicts, which is intriguing. So I don't know the answer to that. If anyone does, come and write to me. But you can kind of see they follow the same curves, but you've got a really large range here. So in reality, if we were to run, EAM 200 times, we might expect a whole range of epidemics. Of course, some of them may not actually be epidemics. They may have their rho value, alpha over beta, initially might not be high enough, so it just dies out. And there we go. But most of them do have some sort of peak. You can also represent that with a few more data runs. So that is some different time steps. You can sort of see how they evolve. That's 0.1, 0.005. It gets smaller. And how about lots more runs? Well, there we go. So this is 200, and I've used a probability map for this. So for every run, so if you could pick a column of time, I said, well, what's the chance of my dead being 52 or 42 or 150? Well, there were none 150, so I've color coded that sort of blue here. And then I can keep going for more iterations than 200. So this is for 50,000. So that's for 200. You can sort of see individual trajectories. And now 50,000 looks much, much smoother. You can kind of just about see these sort of fine fibers here. So you get a sense of the kind of width of your curves. And I think this is important. I think sorry, we haven't had time to talk about COVID-19, but in some ways it's quite nice that that's behind us. So I think I'll sort of leave this with you, because I think, if from the power of hindsight, this is the sort of graph that I think the public should have got, really, for your estimates of infectives versus time, because you don't just want what our predictions are, you want the uncertainty. All right. And so this is like this with anything, like you're predicting the weather, the weather over the next few days is going to be nice and sunny, but plus or minus 10 degrees. Well, that's obviously rubbish, because, that could mean it's really cold and rainy, or it could be a heat wave. Whereas it's plus or minus 1 degree, well, we're like Arizona, it's pretty predictable. So you want the average, but you also want the uncertainty. All right, which is exactly what we do with experimental physics. So here we can talk about, the probability of being beyond our kind of mean curve. And that's, I think, that's certainly our best effort in terms of modelling the EAM system, and all that's written up in the Science by Simulation 1. So I think we'll end there. So thank you very much, Amazeballs, if you have attended all the talks this year. I hope that's been fun and informative. It's slightly different every year. Thank you for your queries. And yes, the emojis have started, the cards to flow up the screen. Marvelous. So yeah, we'll pause that until BFO round 1 training was it for me in September. Do please tune in next week, where Nina and our very able team will sort of talk you through. They are the markers of the challenge. They'll give you some real hints and tips, the sort of things they're looking for. Some of the amazing videos that we had last year, so I think the idea is that we'll have a kind of bronze value one. So what does that look like? What's a silver one? What's a gold one? But also, I think you'll probably realize we have upped the standard a little bit this year. So things that were gold might actually be a silver this year, because we're going for, you have to code up everything to get silver. So hope that will give you a good handle on what to do. And we can the challenge is available to all levels. So if you are a black belt programmer, fantastic, we've got the challenge for you. But if you're completely new to this, then that's also, we really do encourage it. If you think a bronze is what your ceiling is going to be, that's brilliant, because it will get you involved with some coding and certainly some Excel work. So good luck, and thank you very much. Have a good evening.
Can I just quickly add something, just a bit of clarification?
I'll just stop sharing.
Yeah, thank you. Hi, I'm Nina. Nice to meet you all. So I'm one of the markers. I just wanted to quickly clarify. So for now, you have a link to register interest in the challenge. So all you do is input your details. The link with instructions and more information about the challenge and materials and so on. One of the links you might not be able to access, the OneDrive, but then there's another link. So if you go to the Eclecticon, there's a link at the bottom of the page with Challenge 2025. That's the same content as the OneDrive link. So just get your hands on that. About the oversubscription, so if we get way too many responses to that initial form, we will not be sending a link for you to submit your actual challenge to absolutely everyone. We'll just start from first come, first served. So yeah, this form right now you're filling in so that you can receive a link where you will be uploading your challenge. Anyway, next week we'll do a little session where hopefully we'll answer all of the questions about what's expected during the video, how much detail do you have to go through, like do you explain your code, do you explain your paper, what do you show, how do you speak, and so on. So we'll show you a few of the bronze, silver, gold from last year, and we'll clarify things a bit more so that you know what you're getting yourself into. So yeah. I hope this helps.
Fantastic. So just a couple of tips. So it shouldn't we underestimate that. So we've gone for 3 minutes this year. It's been up from 2, but this is not something that's easy to actually put your point across in 3 minutes. Is a challenge, literally. But this is a realistic one. Even if you're doing a multi-billion-pound project for the government, you might have to put your point across in a minute. Why should you justify your funding? So this is good for you. But the quid pro quo is that don't record your 5-minute talk, speed it up, and then submit it. We can tell. Unfortunately, we might have to disqualify if you do that. So please don't do that. I know some of you like watching YouTube on a high speed, but the very best ones have been easily within the time, have conveyed all the information, and have been slick. And a top tip, as I discussed last week, is that often you might want to combine the various challenges. So the middle ones are all about importing a bitmap and then looking at your mirrors and reflections. You could show the code of how you imported and created your app, as it were, and then you could just sort of show various menu options for the different solutions. So lots of students have done that in the past. So that's something you can kind of save time without a loss of clarity. But I really strongly encourage you to rehearse and script your presentation. And it does need to be, if you're in pairs, we need to have roughly evens between the two of you. So I would suggest that's going to be quite a large fraction of your time. So good luck.